How do you do, ladies and gentlemen, and boys and girls? Again, I am Julius Sumner Miller, and physics is my business. And we come to another lesson, so to call it, on heat and temperature. And the title of this one is Thermometric Properties and Processes. Thermometric Properties and Processes. By that I mean, what devices are there? What actions of nature exist for us to tell the temperature of a system? First, I would remind you of what is commonplace in your life. A thermometer, a thermometer. Now, you know what a thermometer is. We have a long glass tube that has some mercury in it, and it is pumped down a little bit and sealed off. And then the mercury expands when there is a change in temperature. And so we say, first, expansion is a thermometric process or property. Expansion. In general, all things expand when heated. Yet it is interesting to discover in a later recitation by me that there are some strange things that do not expand when heated. And I leave it for the moment for you to think about a very commonplace stuff which does not expand when heated. Strange business. So expansion is a thermometric property, a commonplace one. What is another one? Electrical resistance. Electrical resistance is a thermometric property. Now I'm going to do a most remarkable demonstration, and here it is. Supposing I take a coil of wire and connect it in series with, say, an automobile headlamp, and then connect it, as we say, to some difference of potential, like a storage battery, a battery like in your car, and let me have the circuit such that the resistance of this wire and the resistance of the lamp filament is just enough to make the lamp light at normal brightness. Now what do? I am going to heat this coil of wire. That's my symbol for heat. It's a candle, you remember? I'm going to heat it. And what do we discover? An astonishing thing. The lamp gets dimmer, suggesting that the resistance of that coil increases with rise in temperature. Now, for those of you who plan probably to pursue physics further, I will write for you that the resistance at some temperature T is the resistance at 0 degrees times 1 plus alpha delta T, which tells us the behavior of that wire with change in temperature, and this alpha is a certain property of the wire. Let's go down here and see this, because this is a very dramatic thing. Here is the coil of wire, and here is the lamp in series with it, and here is a storage battery, and I'm going to connect this storage battery to the lamp, and you see the lamp lights at what we would call normal brightness. Now, supposing I put some ice on there. I put some ice. Dry ice would be better. We would see the lamp light ever more brightly, meaning that I have cooled the wire and therefore lowered its resistance. Now let us get a feeling for how bright the lamp is. I am going now to heat that coil from below, and I'm turning on some gas here. Now, if we can dim the lights perhaps in the studio. Notice the lamp is getting dimmer and dimmer and dimmer because its resistance is increasing. Let me show you quickly by cooling the wire. Oh, notice of course, the ice is being melted by that hot wire. Notice now how brightly the lamp burns, meaning that the resistance of a conductor increases with change in temperature or rise in temperature. A very interesting thing, very interesting for you to pursue. This alpha is a certain property of metallic conductors. It is called the thermal coefficient of resistance, or the temperature coefficient of resistance. And it turns out to have a value about like this, .00366 ohms per degree centigrade. And so somebody says, Professor, what's all that number mean? And I'm going to tell you an important secret. That number happens to be about 1/273rd. 1 over, and somebody says, oh, that is astonishing, because 1/273rd is the temperature and pressure coefficient of gases, which means what? That electrons in a wire behave exactly like the molecules in a gas. Isn't that fantastic? I want to say that again. The electrons in a wire behave exactly like the molecules in a gas. Who would think that? So, electrical resistance. Another thermometric property. Here is a very strong magnet, and here is an iron bar, and obviously, the bar is pulled onto the magnet by magnetic forces. Now, what would I do? This has to be a virtual demonstration. Here is the horseshoe magnet. Here is the horseshoe magnet, and there is the bar. Now, if I were to do this experiment for real, what I would show you is this. I heat that bar with a burner, and lo and behold, as the bar gets higher and higher in temperature, the magnetic forces are less and less effective, and soon the bar would drop off. That reminds me to tell you, if you should ever visit a steel mill, you will see that when the huge steel slabs are picked up hot, they are picked up with tongs like this, like that. But later, when they get cold, they are picked up by an electromagnet. Do you see that when they are hot, they cannot be picked up magnetically? So, magnetic property is a thermometric process. Another one, thermoelectric power. Thermoelectric. You get the connection? Supposing I take any two wires, two different wires, say copper and iron. Connect one pair of ends, and then connect the other to an instrument which we call a galvanometer. This is an instrument for detecting the existence of an electric current. Supposing I heat this junction. Lo and behold, an astonishing thing ensues. There is an electric current in the circuit which is evidenced by a reading of the meter. Let me show you that. I have here two different wires whose junction is connected right here, and this instrument is a 0 centimeter, and I'm going to heat that junction with a match. Watch it. Watch it. Look at that. Look at that. Now, that scale there reads in electric units. That is, it reads amperes. I want you to see now a thermocouple junction which is connected to a thermometric scale which reads really in degrees. Here are the two wires, and there is their junction. I'm going to heat the junction, and you watch the scale as well as the junction, because another important thermometric property emerges. Watch it now. I'm heating it up here. And now if we can get a look at the scale, you see the scale is going up. The scale is going up. And indeed, this could well be reading, I think it's reading 1,000 now perhaps, if we can get a look at the scale. And so the temperature is going up, and the scale reads in degrees Fahrenheit, 1,000, and now it's about 1,200, and so on. And now, if we had sharpness of eye and could see in the darkness of this room the junction that I am heating with the flame, we would see another property. There it is, I see it very clearly. It is red. It is red. And I have suggested, I'm going to cool this off. Oh, there's a very good question. Why did that sizzle, and where did the noise come from? You see what I'm getting at, boys and girls, and teachers, and fellow Workers, whenever we encounter anything in nature, we should ask, why does it happen? So, the point I wanted to make is that this junction got red as the temperature got higher. So, I'm prepared to tell you that color is a thermometric property. Color. Color. Oh, number 3 is thermoelectric. Number 4 is color. Color. Oh, I left one out, didn't I? I left out magnetism. Magnetism is a thermometric property or process. Color is a thermometric property. Notice, physiologically, when a fellow gets very angry, his temperature goes up and it shows in the color of his face. But here is a better demonstration than that. Here are some colored sheets of paper. Red, white, green, pink, blue, and so weiter, and so on. Now, what would I propose as an adventure for our study of heat and temperature? Take such pieces of paper to the mountain where there is a fresh new bank of snow and lay the papers out on the snowbank. And lo and behold, what would you discover? In the sunlight, let us agree, we would discover that they sink into the snow at different rates. Why? Because they possess different radiation and absorption properties which are thermometric. And I hope you agree that the one that would sink the fastest would be the black. And the one that would sink the least would be the white, obviously. White reflecting all the radiation that falls upon it. Some more at random thermal expansion, about which I shall say more later. Here is a little array of 2 bulbs with a very volatile liquid inside, like ether or acetone, and the vapor of the liquid is in one vessel above the liquid and here in that vessel. Now I'm going to apply some heat from my hand. Watch it. Watch it. Now, the action is not very fast. Not very fast. I had hoped it would be faster, and I'm led to ask, why is it not faster? And the answer is, this little piece of apparatus has been lying here in the studio, exposed to all the radiation from these hot lamps, and so it has come nearly to thermal equilibrium with the surroundings and will not respond too much. But one last evidence of thermometric expansion. You know, if you live in cold climates like Minnesota or northern Canada, that if you have some milk and cream bottles left on your porch in the morning by the milkman, that you find them in a strange behavior at the top, suggesting that something has expanded when it got colder. About this we shall speak more another time when we speak about the strange properties of water. And I shall return another day. How do you do, ladies and gentlemen, and boys and girls? I am Julius Sumner Miller once again, and physics is my business. And we come once more to the subject of heat and temperature. And this program we shall devote to this subject explicitly. How can we produce heat energy? How can we produce heat energy? Now, there are numerous ways which we can resort to produce heat energy. And first, supposing I have some water here, and this is something you must not ever do. Notice the firmness with which I make that sentence. Water. Supposing now I had here some acid of some sort, sulfuric, hydrochloric, some kind of acid added to water. Very dangerous business. The action, we say, is exothermic, releasing heat energy. You must never do it. But what am I suggesting? Chemical action is one way to produce heat energy. Chemical action. Another. Indeed, I'll approach it another way. There are various kinds of energy. Mechanical energy, acoustic energy, electric energy, magnetic energy, electrostatic energy, nuclear energy, electromagnetic energy. All of these kinds of energies can produce heat energy. And so we say that thermal energy, or heat energy, is a degenerate form because all the other forms can go that way to that one. Illustration. Illustration. Here is a cup of tea which is cold. Cold. I want to make that cup of tea proper and adequate to drink. I propose to heat it. How could I heat it? I could heat it by stirring it in this way. Stirring it, stirring it, stirring it. Take me a long time, but I am converting mechanical energy to thermal. Or consider the following. Here is a beautiful one. Acoustic energy. And I have made this calculation. You know that it takes work for me to talk. Indeed, I ate food which has been metabolized, which makes available energy so that I can talk. So, the compressional waves that are emerging here involve an output of energy. I say that if I talked long enough onto that cup of tea, I would heat it up. Indeed, I've made the calculation. Ordinary talk produces about 100 ergs per second. And an erg is about 1/10,000,000th of a watt. So, if I wanted to light this electric lamp or heat that cup of tea, you see it would take several 100,000,000 people talking for a long time, but it could be done. I'm suggesting the conversion of acoustic energy to thermal. Or consider another. Consider another. Here is a slab of lead in which I have inserted a thermocouple. Now, you know what a thermocouple is? 2 wires of different stuff. I could connect this block of lead. There's the block of lead with 2 wires in it. I could connect this to a galvanometer, and I could hit that slab of lead in this fashion, and we would see an amazing thing. This galvanometer would show an electric current, which means that the junction here has suffered some rise in temperature. Or a better one. Here is a nail. I have done mechanical work on the nail. Now I'm going to pull it out. Oh, there it is. I have plenty of evidence that that nail is hot. Mechanical work. Or a better one. I like to do this one because it has much history of an enchanting sort. An electric drill. Hot. The wood chips are warm. And I am therefore reminded that mechanical work arising from electrical energy converts to heat. And I like to do this experiment because it brings to our attention this man, Count Rumford, William Thompson, a Yankee who turned British, who became German, who married Lavoisier's widow, who for the Bavarian government was engaged in drilling cannon and discovered that the chips got hot. And he threw the first light upon that very difficult subject of heat, which was originally called caloric. See, we get the word calorie. Or consider the following. In this tube, I have some lead shot, little BBs. good. Supposing I weighed the lead shot and I took the measure of this length. Clearly, I do certain mechanical work in raising the shot to the top, and then gravitational forces pull it down. The mechanical work I do is converted to heat. I could do this 10,000 times, taking the original temperature, finding the final temperature, getting the difference in temperature, and it is an elementary classroom exercise. If you know the mass of the stuff, the change in temperature of the stuff, the amount of mechanical work that was done on it, W-O-R-K, you could find, and, well, we would find what? The mechanical equivalent of heat. How much mechanical work does it require to produce heat? Answer. Answer. Look at here. This is fantastic. 778 foot-pounds of work to produce 1 British thermal unit. What does that mean? It means that I have to do 778 foot-pounds of mechanical work to produce enough heat energy to raise 1 pound of water 1 degree Fahrenheit. So I suggest, indeed, it occurs to me every time I take a bath, that enormous mechanical work has been required to heat that much water to that higher temperature for me to bathe. And it always brings me to think of that beloved Count Rumford, who married, as I say, Lavoisier's widow. Another. Here is an array of magnets, and inside a coil of wire. And here is a lamp connected to that coil. I'm going to do mechanical work on the coil. It requires a force to turn the crank, to turn the coil, and watch the lamp. Obviously, I have converted mechanical work to electrical energy, and the electrical energy has been converted to thermal energy because the filament in the lamp got hot enough for us to see. It emitted light. Or another wonderful one. Here is a slab of lucite, plastic. And here is a cat's fur. And I am going to do some mechanical work. Here is a metal plate with a handle. I'm going to put the metal plate down on top. I am not discussing the electrostatic changes that are taking place. I'm going to ground the upper surface of the plate. Oh, I felt something. And now, listen, listen, listen. Oh, there was a spark. I'm going to do it again. There's a spark. Indeed, here is a fluorescent lamp, and I think that if we quieted the lights in the studio, you will see that I have produced enough electrical energy. We need all the lights, I think, in the studio to see the lamp. Yes, I saw the lamp flash, but of course the lamp is too much lighted by the lights in the studio. Let me take another lamp. Here is a tube that is filled with neon gas, and I want you to see the flash of that tube. Watch it. Yes, I saw it. There it is. There it is. I'm going to do it again. And what have I suggested by this adventure? I have suggested that we can do some mechanical work on that dielectric, which is the slab of lucite, give rise to a separation of the charges, and then draw electrical energy from this system. And here is a comment about which I shall speak more adequately when I do a program on electrostatics. I can continue to draw this energy from this system forever without any diminution in its availability. That's a fantastic thing. Now somebody says, did you say, Professor, that you can continue to draw energy from this system forever without any diminution, any lessening in the amount of it? And my answer is yes. And forever is a very long time. Consider now another little classic, quite enchanting. There arises often this little problem. Here is a perfume bottle, and the glass stopper is lodged in it so firmly that it cannot be removed. Now, what do I propose to do? I propose to get out the stopper. There are all kinds of methods for doing this. Heating it in hot water, heating it with a flame, pouring some solvent down through where it fits. But here is a wonderful way to do it. A piece of string wrapped around the neck and such action. Now, what am I emphasizing in all of this? I am emphasizing a very important subject, which is a terror for the human race. Friction. Friction. And what must we say about friction? We must say this. We spend untold measures of money and effort to minimize friction, reduce it, get rid of it. But is not this something to think about? If we were successful in eliminating friction, there could be no motion of any sort. Meaning that if friction were at this instant annihilated, undone, disposed of, I could not move from this place, except perhaps upward. Oh yeah, I could do that, but I couldn't go forward. Supposing I did go forward, I could never stop. So if now, at the switch of my fingers, friction were eliminated from the earth, all motion would be quieted. Every automobile would be brought to rest. All the ships on the sea would stop moving. Maybe the astronauts would keep going because they are in empty space, and having once acquired the motion, they go without effort endlessly. Now, where are we? Oh, more on the matter. Production of heat. Bicycle pump. You know, you connect it to your bicycle tire or your automobile tire, and you pump, and what happens? The piston gets hot. Heat energy converted from mechanical. Or consider a simple one that is most dramatic. Here is a paper clip. What shall we do? It is now at room temperature. I bend it. I bend it. I bend it. Uh-oh. I cannot hold it anymore. It is too hot. And what I would ask you to think about is the astonishing behavior internally of those little molecules and atoms of stuff which are put into fantastic agitation. And this is a mode of motion which describes this thing called heat. And I thank you for listening. How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller once again, and physics is my business. And this time, our special business is the thermal expansion of stuff. Notice how I use that word. Thermal expansion of stuff, especially concerned with solids. Solids. Remember, to the best of our knowledge as earthbound creatures, all matter is either solid or liquid or gaseous. I say for earthbound creatures, there is a new kind of stuff now in the laboratory, as the British call it. Plasma, electrically charged stuff. And indeed, there may be stuff in a different state elsewhere, which travel to planets elsewhere and stars remote may reveal. But anyway, the thermal expansion of solids. A classical experiment which is not ever really properly explored, as we shall see. The classical ball and ring. Now, what do we do usually? We show that this is a brass ring and this is a brass sphere. They are metals. They expand when heated. We show that the ball cannot pass through the ring. the hole. This suggests very clearly two things. Either the hole is too small or the ball is too big. And because I'm a charitable man, I'll let you think whichever you wish. The hole is too small or the ball is too big. So now what do? We will make this a virtual demonstration and imagine its consequences. We heat the ring in a flame. We heat the ring in a flame of a Bunsen or Mecca burner. And if I do it long enough, I can then pass the ball through. Uh-huh. So somebody says, I understand that. The hole got bigger. The ring got bigger. Of course, these things may be true. Now, as all of you know, I am not so much interested in what we know as I am in what we understand. This is much more important. Accordingly, if we understand what has happened here, the following question can be answered. I have here some metal plates. Here is an aluminum plate with a little hole in it. Here is an aluminum plate with a little hole in it. Here is a plate. Here is a plate. It happens to be rectangular or square. It has a teeny-weensy hole in it. I can see the light. Question. Problem. I heat these plates uniformly. How could I do that? I could put these plates in the oven of my stove at home and heat them. So they are heated everywhere uniformly. Some of the plates are circular, some are rectangular, and they have little teeny-weensy holes. Question. When the plates are heated, what does the hole do? I'll give you some choices. One, the hole does nothing. That's a very good thing to have happen, because I plan in the future to do a lesson on relativity where we will see that Einstein took hold of an experiment whose results were nothing, and he made relativity of it. So nothing is important. So the holes do nothing. The holes get bigger. 3, the holes get smaller. Or I'll let you make that one smaller and that one bigger. I don't care the order. So, what do you think the holes will do? Do nothing, get bigger, get smaller. Now, I am led irresistibly to refuse to tell you, because it is more exciting if you engage yourself and your teachers and your classmates and your mothers and fathers and uncles on the question, what does the hole in this plate do? Oh, says some, say some, gets bigger. No, it gets smaller. So I'll tell you the best way to learn the truth of matters. Those of you who think one thing should get together with those who think the other and argue it out. And then, of course, you can do the experiment. One more exciting little dramatic investigation regarding thermal expansion of solids. Here is a ring of metal, a ring, and it has a diameter of its own stuff. Not welded or soldered or brazed, but part of the ring. Let us say that this is a very good ring, a very good one, a very good one. And I put this in my oven and heat it. Question, does the ring stay circular or does it warp? Does it stay circular or does it warp? And would you believe it, boys and girls, I have gotten tens of thousands of letters regarding this little inquiry, in most of which the answers were wrong. But anyway, let's consider another. A bimetallic strip. Here is a strip of stuff brazed to another strip of stuff, and they are not the same kinds of stuff. Accordingly, they have different coefficients of expansion. I'm going to heat this bimetallic strip here in a flame and watch what happens. Watch. Look at that. Look at that. It is bending. Bending. Now, I'm prepared to tell you that one side is brass, and the other side is iron. And I want to know, did it bend on the iron side, toward the iron side, or did it bend toward the brass side? And so you see, I am raising some exciting little inquiries. More on expansion. I have here 2 pieces of glass rod, so it looks. 2 pieces of glass rod. I assert, however, that one of them is glass and the other is quartz, and I'm going to heat them in this flame. And I want to show you a very remarkable thing. I'm heating them both, the glass and the quartz. I'm going to heat them until they get red hot. And remember, color is a thermometric property. And then I'm going to immerse them while red hot in a beaker of ice water. And what would you expect? Would you not expect them to shatter? Let's assume they are heated enough. I see some yellow flame there, which is characteristic of sodium glass. Watch it now. Now let's, I call to your attention the fact that they have both shattered. Whereupon I say as follows. I made a little mistake. I thought one was quartz and the other was glass. So you see what experiment in the laboratory means? Sometimes things go as you wish and sometimes they do not. But what I wanted to show you is this. The glass one would indeed have shattered into 1,000,000 bits. Here, I'm going to show you that. Watch, watch. Oh, look at that. Oh, look, see, 1,000,000 little bits. But the quartz one would not, because quartz has a very low coefficient of expansion. Now, here is another demonstration, which you can do for yourself. Here is a metal rod, and here is a little L-shaped wire, which marks against a certain scale if we can get tight on it. Now I am going to, oh, no, I thought my flame went out. No, I am going to heat that. I'm going to heat that, and if we can see the scale right tight, at right angles to it, I hope you can see. I'm sorry, we had a little disaster. I turned on the gas too much. Do you see the adventures which can come when we do experiments in the lab? No hurt, the hose just blew off. This is experiment. Consider another. Here is a long rod, aluminum. Here it rests against a registering meter, and I am going to heat this rod. If we can get a view of this scale here, very closely, it reads 0 to begin with. I'm in a little trouble because I don't have my heat source. I detect a slight change in the length of this rod. Ever so slight, but nevertheless it exists. So I have an interesting little question for you, a wonderful question. Consider a railroad rail that runs, let us say, from Los Angeles to San Francisco. That's about 400 miles. A steel rail. Supposing that was one rail, and supposing we assume that between the coldest or lowest temperature and the highest change in temperature, we might have 25 degrees change in temperature between the lowest and the hottest in the course, say, of a night. Question, how much do you think that steel rail would expand? 400 miles of it. Now, you know the steel rails are laid so that there is a little gap between successive ones. That little gap is very small indeed. But here is something for you to calculate. The steel rail, one rail, between Los Angeles and San Francisco being 400 miles long, suffering the change in temperature I have suggested, would expand, what do you think, a foot, 10 feet, 50 feet? No, I'm going to tell you, 600 feet. 600 feet. Isn't that fantastic? So those little gaps between the successive rail lengths between here and San Francisco, those little gaps add up to 600 feet. That's absolutely astonishing. More about expansion. A wonderful thing. How many of you have seen popcorn? Everybody in the world has seen popcorn. Here is some popcorn. Now you know what you do. You apply some heat to the popcorn, to the dry, lifeless, dead, inert popcorn. But I would remind you, it is not dead, lifeless, and inert. If this is put in the good earth, and it has the right change in temperature, the right dark and the right light, the right heat and the right cold, the right wet and the right dry, it will sprout and beget itself millions of fold. So it is not lifeless. I ask, when I heat that and the corn pops, why does it pop? Why does it burst so big and beautiful? Answer, there is, however dry it is, there is some water in it, ever so slight a bit. And when that water is heated to the state of steam, it expands 1,700 times. That is, if I have a little droplet of water in there, so big, when I heat it to steam, it is 1,700 times bigger. And I say that's fantastic. One final little inquiry, which you can do yourself. Here is a flask which is filled with colored water and with a one-hole stopper and a glass tube, and you see the level of the water to this place here. Now, you know that if I mechanically squeeze the wall of the flask, the level goes up. If I mechanically squeeze the small edges of the flask, the level goes down. Down, up. Question, supposing I heated the walls of the flask, heated them, would the level go up or would it go down? And so I have left you with a number of exciting and dramatic and stirring inquiries concerning the expansion of stuff. And I thank you for listening. How do you do, ladies and gentlemen, and boys and girls? Once again, I am Julius Sumner Miller, and physics is my business. And this time, our principal concern is the thermal expansion of stuff, more exactly, gases and liquids. In an earlier program, we addressed ourselves to the expansion of solids. Now, the expansion of gases and liquids is an enchanting subject, because it involves some strange and uncommon things. Let me illustrate with something you already know. Supposing you start out in the morning of a hot July day, and you have your automobile tire, here's the valve stem, inflated to a certain pressure, let us say 35 pounds according to the gauge. Now you drive along the hot road. The air is hot, the road is hot, the ground is hot, you're hot, the tire is hot. The air in the tire is hot air in the tire. You put your hand on the tire, woo, it's very hot. So you're sure that the air in the tire is what? It's hot. Now you get worried. Pressure may be getting too much because of friction and rise in temperature. Pressure may be getting excessive and the tire may go boom. So what do? You stop, you take off the valve cap. It's not a very proper thing to do, really. And you depress the valve stem. Out comes the air. And remember, the air in there is hot. But what does it feel when it comes out? It's cold. Hot air coming out is cold. I'm going to prove that. I have a tire over here that's filled with air, filled, I say, to a certain pressure, 35 pounds or so, and this has been in the studio being heated by the light so that the tire is hot. The air in the tire is hot. Now I'm going to depress the valve stem. So That air is cold. And I say that's a considerable dilemma. Hot air coming out cold. But that isn't so dramatic a thing as the following. You know what a strange kind of creature a physicist is. I'm a physicist, and look what I can do. I'm going to blow air from my lungs, and the air in my lungs is hot air. I'm going to blow it on my arm. Hot air. Hot. Now I'm going to blow it. It's cold. There you are. I am really a rascal. I can blow hot and cold. Same air. Hot. Cold. This is a very difficult subject. Thermodynamics. Wicked and brutal and mathematical. And I'll leave it for you to do some studying on it, because it would take me some hours to make clear what I'm talking about. Let me illustrate it another way. Here is a CO2 fire extinguisher. I'm going to let some of the gas out and watch what happens. It is so cold that we see snow. There it is. There it is. CO2 snow. Let me show it to you another way. And this involves Newton in a beautiful way. Here is a system with a horizontal arm that moves freely on a good bearing. Here is a chamber, and that chamber has a barrier on the backside. Yes. Now I'm going to go back the other way, and I'm going to put a CO2 cartridge. Remember, gases. Gases. I could put all the gas in this studio in this little thimble. On the other hand, if I open this, the gas in here could fill the studio completely, which suggests the property of gases. I'm going to put this chamber, this CO2 cartridge in there, and I'm going to make a hole in it. And remember, this is warm. Whole thing is warm. I'm going to make a hole in it. Better be sure I don't collide with anything here. Now. I'm having a little trouble. Just hold still. Just hold still. Just hold still. Having a little trouble. There it is, there it is. There's Newton's third law, of course. And I'm going to stop it. But my interest is not the mechanical part, but rather, this is ice cold. Not only that, but I see some frost on it. I see some frost on it. The gas coming out was cold. This is absolutely astonishing. Expansion of gases. Their temperature drops on free expansion. Another demonstration, which is most remarkable. Remember, I'm talking about the expansion of gases and liquids. Now, water has strange properties, and I'm going to do a program, a show, a lesson on water alone. But for the moment, here is a chamber made of 1/4 inch thick iron. Now I'm going to imagine that we fill that completely with water. Completely. That means that the occluded gases in the water must be driven off. We could do that by warming the water gently. Now I'm going to stopper this up with a screw cap very tightly, so that we have water in here and nothing else, no air, no other gases. Now let us imagine that I take this iron bucket and I put this ice bomb, as we call it, in there, and then I load this with ice, to which I could add some salt, because salt depresses the freezing point. You've made ice cream, I'm sure, by adding salt to ice when you ground away at the cream. Now what happens? The water gets colder and colder and colder, and now a strange thing. We cool it down from 8 to 7 to 6 to 5 degrees centigrade, I'm talking. And now at 4 degrees centigrade, it has its maximum density, which is a strange thing. And then we go to 3, colder, 2, colder, 1, colder, 0 degrees, and it freezes. Remember, It was most dense at 4, but it freezes at 0. So the water in there freezes. Now, what happens to water when it freezes? It has, as we say, anomalous properties. Strange and uncommon behavior. It expands. And the forces of expansion are thousands, tens of thousands, hundreds of tons. And this is what happens to that bomb that I have just described. Rent apart. Indeed, it is very dangerous to do this experiment because sometimes the pieces of the iron chamber pierce a hole right through the wall of the bucket and could hurt you. This suggests the enormous forces when water freezes. Now, expansion. Consider these two little chambers that I spoke about before on an earlier program, and they failed to work as properly as I wanted because they were at too high a temperature because of the lights in the studio. A volatile liquid, let us say acetone or ether, the chambers have been drawn down a little and evacuated so that I have the vapor of the liquid there. Now I'm going to apply some thermal energy from my hand to the vapor right there. Watch it now. Look at that. There it is. Notice the tremendous increase in pressure of the vapor. The expansion of the vapor drives it over. Here is a bigger one of the same thing. Oh, look at that. Look, isn't that incredible? Look at that. I had this in a chamber in this bucket with ice so as to cool it down. Let me warm it up. And look what's happening. Look what's happening. The increase in pressure, the expansion of the vapor, driving it over. There it is. And doing enormous work, of course, in raising this liquid above the zero potential plane. There it comes back, there it comes back. And I shall not worry you further with that. Let's take another demonstration. A balloon. Some air in it, and then it's tied off. I'm going to try this. This is wonderful because often it doesn't work, and I like demonstrations that don't work. Here is a mecha burner, something like a Bunsen burner, fed with some propane gas, and here is a flame there. I'm going to try to heat this, and if we can get close with the camera, I hope to see an increase in the size of this balloon. Oh, well, whether there was an increase or not, I don't know, but it was fun. You see, people, ladies and gentlemen, and boys and girls, I said what? I said it was fun. I can do this work only because it's fun for me. And that's why it has been so easy to do. So I suggest that some necessary ingredients of your life and work be imagination abundant, good health, of course, you need much of, otherwise you are useless, but then you must have fun at what you do. Consider this experiment. I call this my Julius Sumner Miller earthbound rocket. Here is a steel pipe, one end of which is capped off very tightly, steel pipe, and it's on a wheeled affair so it can roll. Now what do? I put some dry ice in there. You know what dry ice is. Dry ice is solid carbon dioxide, solid CO2. I put some in there, jam it in. Then I put in this stopper, tightly fitting. Then I let it stay here on the table and let some time elapse. Now, you know what happens to the solid CO2? The solid CO2 goes to gas. As a matter of fact, it has strange properties because it doesn't go through the liquid state. It goes at once from the solid to the vapor. And we say that it sublimes or sublimates. Let's think of another thing that does that. Oh, camphor. You put camphor, what is camphor? Dichlorophosphobenzene or some such stuff. You put that in your clothes, in your closet, and it disappears without leaving any sign of wetness. So anyway, the CO2 in there goes to gas. Gas, pressure. What happens? Out goes the stopper, boop, and this earthbound vehicle of Julius Sumner Miller vintage goes the other way. This, of course, is a demonstration of Newton, but what I'm talking about here and now is the tremendous expansive properties that arise from the expansion of the CO2 vapor. Now, I had set up here a demonstration commemorating the work of our beloved Michael Faraday, his air thermometer, which I invite you to do. We are having a little trouble with it because we are working here under uncommon circumstance with much light in the studio. But here is a flask and a one-hole stopper and a tube, and the lower end of the tube is in this colored liquid. Now, what did Galileo discover? Galileo discovered that the level of the liquid comes up and goes down according as the temperature in this goes up and down. Now, strangely enough, you see, he was not measuring temperature change, but rather pressure change. And so I hope you will investigate the wonderful work of Galileo Galilei, and I thank you for watching.
.45 and .49.
How do you do, ladies and gentlemen, and boys and girls, and teachers, and men and women, and people? I am Julius Sumner Miller, and physics is my business. And once more we come to the subject of heat and temperature. And in this lesson, in this lecture, so-called, I address myself to what I have entitled here, the strange thermal behavior of ice and water. Very strange. And indeed, it is a marvel to contemplate because the behavior is so anomalous, so strange, so uncommon. Consider the following, which is a little mathematical, but very necessary to our understanding. Supposing I take a glass beaker, just a beaker, and this will not enter our discussion. It is simply to hold what I want to hold. And I put 1 gram of ice in there, one hunk of ice weighing a gram, and I put a thermometer there, and the thermometer reads 0 degrees centigrade. And the stuff is solid. Now, what do I want to do? I want to add some heat energy to there. Now, you know how I add heat energy? I put a candle under there, and I add heat. Now, what happens? As time goes, we see less and less ice and more water. And indeed, after a little time, I don't have a gram of ice, but I have 1 gram of ice water, and what is the temperature of that ice water? 0 degrees centigrade. And how much heat have I added? I have added 80 calories. 80 calories. Now, this should make clear the difference between heat and temperature. I have added 80 calories to a gram of ice, and I get only a gram of ice water with no change in temperature. Now, let me take that gram of ice water at 0 and add some heat to that. Now, what happens? The thermometer goes higher and higher and higher, and pretty soon I have 1 gram of water, and it is now at boiling, so call it 100 degrees centigrade at 1 atmosphere. And how much heat have I added? Well, I have added to the 1 gram of ice water at 0, I have added 100 calories, 1 calorie per gram per degree, so plus 100 calories, and what have I got? I have gotten a gram of water at 100. So you see, here there was a change of state from solid to liquid. No change in temperature. Here there was a change of temperature. Ice water, water. So change of state requires, enlists, encounters no change in temperature. Now let me add some more heat to this. More heat to this. Now you know what happens. I add more heat to 1 gram of water at 100. There's less and less and less and less and less and less. And pretty soon there's no water. It is all water vapor. All water vapor. Notice V-A-P-O-U-R or P-O-R. So it's all in the gaseous state. And how much did I have to add? I had to add 540 calories to vaporize that 1 gram of water at 100 and make it 1 gram of water vapor. Do you see then the essential properties of this strange stuff? Change of state, no change in temperature, which suggests that to carry, as I put it here, 1 gram of ice from 0 degrees centigrade to 1 gram of water vapor at 100 requires enormous heat energy, and therefore the liquid state is more energetic than the solid, and the vapor state more energetic than the liquid. Now, let me show you. Here's an illustration of it. Here is a vessel with ice and water, and this is in the hot studio, and the thermometer reads, let me read it. It reads 0 degrees centigrade because it's been here a long time, and it'll read 0 until all the ice is gone. Consider the following. Here is a glass such as you would have on your dining room table with a coaster, which coaster we shall see we don't need, and I am going to fill this right full to the brim with ice and water, right full to the brim. Full, full, full. Well, I can get a little more in there. I can get a little more in there. I don't want it to overflow now. Oh, there it is. Good. Now, is not the ice above the level of the water? Sure it is. Question. As time goes in the studio here, that ice is going to melt. Will the water overflow? No, no. Because, as you know, 1.1 cubic centimeters of ice gives us 1 cubic centimeter of water. That's why an iceberg is mostly below the level of the sea. About 9/10 of it below the level. Another wonderful property. Oh, we've got to get over here. Here's what I'm going to show you. Let us take an enormous cake of ice, big one, and put a wire around it, and put some weights on the wire. Weights. Now you know what will happen. The pressure of the wire being very great, because the area is very small and the load very large, the wire will cut into the ice because it melts it. Now, as the wire cuts into the ice is really melted under the wire. Then the water that results from this melting ice creeps up on top of the wire and freezes again. I'll show you how we do that here, and you can do it for yourself because it's a wonderful thing. Here is the wire put around, and let me turn this around perhaps another way. You can see the 2 weights here hanging and the wire. And now the wire will embed itself into the cake of ice and take such a shape in turn, in due course, such a shape. And I always ask students, what is the shape of this curve that the wire takes? And I'm going to give you a secret. It is a curve of least energy, and I think it is a catenary, C-A-T-E-N-A-R-Y, which is quite like the curve that the big transmission cables and chains hang in when they hang freely. Now, what's the essential thing to be said? When the water that results from the cutting wire refreezes, the ice is stronger in this place than elsewhere. Is not that an amazing thing? Now, remember, I said that the pressure of the wire melted the ice. What does that remind me of? Have you not made a snowball out of snow, soft and wet, and you squeeze it, and you squeeze it? Yeah, I have some ice here. Squeeze it, squeeze it, squeeze it, and what happens? The snow melts under the pressure. It melts. And then when you let up the pressure, doesn't it freeze? So rather than having a snowball of snow, you've got really an ice ball made of snow that was melted by the pressure and then refroze. Look at here. No water will overflow. But now, much more enchantment in this exercise. I have an after-dinner trick for you. Notice I said trick. I never like to use that word because none of these things are really tricks. They are engagements with nature, and there's no trickery at all. Question. I have here some ice in my drinking glass, and I hand my neighbor at the table, my visitor, a little piece of string about 3 inches or 4 inches long, and I say to him, with such things as are on the table, get out a piece of ice. Get out a piece of ice. Secret. Watch it. I'm going to wet the piece of string, just wet it and lay it on that piece of ice in there, and then I'm going to take the salt cellar and sprinkle some salt on there. And then I'm going to let things rest. I'm going to let things rest a little while. Now what is happening? The salt has depressed the freezing point so that some of the ice is melting. That ice which melts, that is the water from it, now refreezes. And if you will give it your strict attention, I think you will see that the string is fixed to the ice. Watch it. Watch it. Watch it. There it is. And I say, that is a wonderful thing to contemplate. Indeed, I'm so enchanted by it, I'm going to do it in this big dish, which is filled with ice, and see if I can't lift all of it out. Now, what are we saying here? The strange behavior of ice and water. Now, while that is taking hold of its affairs, you see, nature often requires, and nature, remember, when I say nature, we must spell it with a capital N. Nature. Nature sometimes takes a little while for her actions to occur. Let me try this. Watch. I'll let it go a little. But while we're waiting, it should be obvious to all of us that these bits of knowledge which have been gathered up over the centuries have been done, discovered, explored, inquired into, arrived at by strange and uncommon men. And I want to look at some likenesses of some of these, and we should pay them tribute constantly for the great industry that they gave the subject. Let us look here. Ludwig Boltzmann. Boltzmann. Let us look at that man. Incredible. And now I would say to you, should you go to Vienna where he was a professor, there in the quadrangle at the university you see a bust of Boltzmann. And I remember coming upon it and thinking, the man is nearly breathing. It was so alive. Let me try my ice thing. Watch it. Watch it. Watch it. I'm in a little trouble, but there it is. There it is. The ice fixed to the ice because the salt melted some and then the water refroze. Let us take another look here. Sadi Carnot, a young Frenchman, a French engineer, who investigated the properties of heat and temperature, much to his credit and to the credit of France. Or James Watt. Now, we all associate the name James Watt with the steam engine. And what is the story? As a little boy, he saw the kettle on his mother's cook stove popping around, at least the cover of it, and was led to contemplate the consequences of this. Or, here is a wonderful one. James Prescott Jowl, whose father was a brewer, and he was led to contemplate some of the properties of heat and temperature, and indeed made a wonderful investigation. He went to the falls in France known as Chamonix with a long thermometer, and there he measured the temperature of the water at the top of the falls and the temperature at the bottom, suggesting the idea that work had been done and the temperature of the water had been raised. And now, for boys and girls everywhere, we must not escape taking a look at young James Clerk Maxwell, the young Scot, whose fondness, let me say, was playing with tops in his later years. So do you see, here was a great intellect whose diversion from his intellectual labors was playing with spinning tops. And I hope you engage in the same, and I shall see you once more. How do you do, ladies and gentlemen, and boys and girls? I am Julius Sumner Miller, and physics is my business. And my special business today is this subject: the transfer of heat energy by the mechanism of conduction. Conduction. Very important word to know the meaning of. And I invite you to look it up, because its Latin origin is very important. Conduction. Consider the following. An experiment which we will imagine. Here are two rods. One is copper and one is iron, and they are fixed together very tightly at one end. And I am imagining that I am doing the classical experiment that Ben Franklin did on his investigation of heat transfer by conduction. We will imagine that I put this junction in a pot of hot oil, just like that. And I hold on to the remote ends of the bar as I am doing. And lo and behold, in a short while, a strange thing is witnessed. One of these feels hotter than the other, and sooner quicker, which means that one had thermal conduction at a greater rate. I invite you to do this, using a pot, say, of boiling water, and you will find a strange thing, that the conduction along copper is about 10 times as fast as along iron of the same size rod. Consider another wonderful experiment. I'm going to light my gas burner here, which perhaps I should have done already. There's the burner. Now what do I have? I have two rods, a shiny metal one and a wooden one, tightly fitted at a junction here. Now, around that pair, I have put a sleeve of paper. Here is a wooden rod, there is a metal one, and I've put that sleeve of paper tightly on that junction. And I'm going to put this junction in a flame of a gas tank, gas burner. And a wonderful thing will happen if it does as I want it to do. And if it doesn't, well, then somebody says, "Oh, Professor, the experiment failed." But experiments do not fail. I must provide nature exactly as she requires, or she won't do what I want her to do. I'm going to do it. And watch now. Watch a wonderful thing. A little... Yes, there it is. There it is. I want the camera to get it tight. Do you see a very clearly bounded line? Beautiful. And what do we find? That paper scorched on the wood side, but not on the metal side. Why? Because the metal is a good conductor, and it took the heat energy away and did not allow time for the paper to scorch. Now, next beautiful thing. Here is a little paper cup. I'm going to put a flame under that paper cup, and as anyone in his right mind would say, "Professor, that cup is going to burn." Of course it's going to burn. There it is. It's burning up. It's burning up. As one would say, its kindling temperature was raised. Oh. No hurt. No hurt. That's a pretty thing to see, though. I like that. Look how nice and shapely it still remains. Now what am I going to do? I am going to fill another identical cup with water. I'm going to fill a very same cup with water. There it is, right filled. And I'm going to put this flame under that cup. And imagine what we will witness. We will witness this, that water can be boiled in that cup without burning the paper cup. except at the rim where the paper is doubly or triply folded and therefore very thick. So let's go on with some other matters while we are waiting for that. Notice, the housewife does not have to have metal dishes to cook in. She can cook in a paper cup, which is an idea for conserving or conservation or something. Let's look at that. Let's look at that again. That water will shortly be boiling, and I can boil the water away without burning up the cup. Question regarding a thermometer. Notice, thermometer. Yes, that's what it is. I have a thermometer. Question. Supposing I had here a glass of very hot water. Let's imagine. You see, imagination. I must emphasize that again. Wherever is my pen? Imagination. A very necessary ingredient of your life and work, especially if you're going to be a physicist. Here is a thermometer. There is a glass of hot water. The thermometer reads the room temperature at this moment. Question. I submerge it quickly into that glass of hot water. What do we see first? Very quickly first. Answer, not usually given. The answer is this. There is a drop in the reading of the thermometer. It reads less. Why? Because the glass bulb was heated first by immersion in the hot water. The glass bulb expanded and the mercury level dropped. But now after a while, when the heat energy has been conducted through the glass into the mercury, then up goes the level. One other question while I'm on a thermometer. Why is the bulb cylindrical instead of spherical? Why is it cylindrical? Very good question. So you notice my philosophy here, people. Teachers, mothers, fathers, young and old, children, students. Not to teach you any physics, but rather to show an abundance of demonstrations which are enchanting and dramatic to witness. Let me consider, look here. Let's look at that again. The water is boiling fearfully fast, bubbling away, and yet the paper cup remains nearly with immunity. Let's go on. Here I have a cigarette. Let me light this cigarette. Notice I don't know which end to light, but I'll light cigarettes. Now, I have done this already. I laid the cigarette on this wooden block. And do you see what happened? The wooden block got scorched. We don't use wooden blocks for for ashtrays. We use glass for ashtrays. Why? Because when the cigarette, if left to its own, forgotten, let us say, when the burning gets to the glass conducts the heat away, and the cigarette probably will go out. Let me illustrate that. Here is a beautiful demonstration for you to do. A fork and a spoon, which I lodge together in this manner, and then I'm going to put a match there. Notice I'm trying to work fast and probably will get it all fouled up because I'm working fast. And here is another match, and watch what I'm going to do. Watch. That's a beautiful thing. Notice how stable that is. Notice how stable that is. That's terrific. If we can get a tight shot right on that. Right on that. Now I'm going to light both matches. Just give me your attention a minute. I'm going to light both matches. Question, what will happen? Answer, I suggest nothing will happen. I suggest nothing will happen. Why? I'm sorry. I blew out that match and I shouldn't have done that. Watch it. Both matches will go out. Why? This one will go out when the flame reaches the glass, and that one will go out when the flame reaches the spoon. Well, I hope it doesn't work. And then you'll say, well, it did. Just give me your attention, boys and girls and ladies and gentlemen. Do you see? It nearly didn't do what I wanted it to do. And I urge you, well, it didn't do what I wanted it to do. And I don't want you to say that the experiment failed, because it did not. I did not make the necessary provisions for nature. All right. Next question. Beautiful for the housewives, children, mothers, fathers, teachers. Here are some small potatoes. Let's imagine we have put them in the oven to bake, and they are nearly all baked. Dinner is about to be served, and knock, 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 some company, unannounced and maybe unwanted. You have to bake some potatoes quick for them, and all you have are some big ones. Now, you know these will take very much longer to bake than these small ones. You are not allowed to cut these, but you want them to bake quickly. Question, how will that be done? Wonderful, wonderful. Just take a couple nails like this, 80-penny spikes, bang like that, and bang like that, and 2, 3 more, and put them in the oven. And are we not agreed that the thermal conduction of this iron nail will transfer the heat energy to inside the potato, and it will bake with all quick dispatch? Right. Or, again, for people who eat, flesh eaters, carnivorous human beings. Question, let me imagine that I have 2 identical roasts of beef. Absolutely identical in every respect except that one has a bone in it and the other does not. Question, what is their rate of cooking when put in the oven? Answer, the one with the bone obviously will cook the faster for very obvious reasons. Is not bone a very good thermal conductor? Indeed, it is. Apart from that, I would like to lecture for about a half an hour on the beautiful virtues that this bone possesses. Inside, for example, the marrow, a blood factory which keeps us going. Wonderful thing. So think more about the virtue of a bone. Or consider this. Ho, ho, let's get back on there. Let's get back on there. Camera, quickly, get on the water in the cup. The water is nearly all boiled out, and the cup is still not burning. And I say that's remarkable. Or, give me your attention for another dramatic experiment. Here is an asbestos glove. Notice. Notice. With absolute immunity. Why? Oh, I'll let that go, because when all the water is gone, the obvious consequence must ensue. The paper then will reach its kindling temperature and conflagrate, as one would say. Another wonderful demonstration, thermal conduction. Imagine that you get up in the morning, put your feet out of bed, and put your feet down on the floor. Do you not prefer to put your foot on some deep, heavy, matted, stranded woolen rug rather than on a bare floor? Obviously. Why? Consider the following. Here I represent a bare floor, and here I represent a deep knitted rug, a braided rug. I'm going to do as follows. Right here and now. Feels cool. Oh, that feels warm. When, in fact, they are both at the same temperature, but this conducted the heat away at a much more rapid rate, and therefore, it felt cooler. More than that, illustration. When you get up in the morning, if you don't have a rug near the bedside, what do? Don't you turn your footsie-wootsy on the side, sort of? Why? To make less area of contact, so less heat energy will be conducted away. The same thing happens here. I have a metal faucet. I have a tabletop. I put my hand on the tabletop, feels warm. I put my hand on the faucet, feels cold. Oh, no. They are the same temperature. This, however, is a good thermal conductor and took the heat energy away. Another remarkable demonstration. Here it is. Let's see. Oh, yes, notice. I'm going to show you. The water is nearly gone, but the paper cup is not burned. Let's get on to this one. Here is, no, I can't do it, I don't think. Here is a hub with some metal spokes, all different materials. If I heat the metal hub, would I not find that the different materials conduct the heat away at different rates? So our show has been on the transfer of heat energy by conduction, and I thank you for watching. How do you do, ladies and gentlemen? I'm Julius Sumner Miller, and physics is my business. And my special business today is this subject, the transfer of heat energy by convection. Convection. On an earlier program, I talked about conduction. And here I have taken a piece of clothesline and set it afire, so to say, in a burner, and then shut out the flame, so it is giving me a lot of smoke, abundant smoke, and I've got a real smokestack there, as you see. Now, let's look at this mechanism. Here in this chamber is a candle, a lighted candle, and smoke is coming out of here at a vast rate. Fantastic. I think you can see it. Now I'm going to put some covers on, a cover on that chimney, and the smoke is trying to come out here, but not so well. And if I let this stay for a while, I'm sure the candle would go out. Most assuredly, it would go out if I covered both. Now, watch. I'm going to take both off. Do you see? Not quite as well as I'd like it, but I'm going to do it again. Watch it now. Watch it. Watch it. Now I'm going to take this one off, this cover. Watch. I assert that the smoke is falling down. Very little of it is coming up. Very little of it. This is a little different. Oh, there it is. Let me do it again. I'm going to fill this stack now. Watch it. Watch it. Now I'm going to take that cover off. Watch it. Yeah, there it is. There it is. So you saw smoke go down, fall down. This is a wonderful thing. I'm going to pose a little problem for you. Here is a house with a smokestack. I say that on some days I see the smoke come out and go up, 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 up. Then there are other days the smoke comes out, just out of the chimney, and falls down, down, down to the earth. Question, on what kind of day does it do the one, and on what kind of day does it do the other? Well, I'm going to help you a little bit because it's a strange business. It goes up, up, up on a dry day, and it falls down on a damp day. What does this tell us? It tells us that damp air is not as heavy as dry air, and therefore does not provide the buoyant effect necessary to lift the air up, the smoke up. And this is a fantastic thing to say that wet air is lighter than dry air. It has water vapor in it. Wouldn't you think that it would be heavier? But it is not. Now, while that's smoking, here is another. I have a framework, a closed rectangle of glass with some water in it. I am going to put some food coloring in this corner of the framework. Watch it now. Some food coloring. There it is. And you will see it drift down, diffuse down, gravitate down in a wonderful way. Look at it. Look at it. Look at it coming down. It's coming down. It's coming down. Now I'm going to apply some heat to this tube. Watch it now. You see the coloring, which is heavier than water, drifting down and diffusing. Now I'm going to apply some heat energy here. And I say, color, go back. Color, go back. That's what I command it to do. Oh, it's coming down. It's coming down. But I say it should go back. Watch it now. Watch it. Aha! There, it's going up. It's going up. And it's going to come down here. So I'm going to play the burner, the flame on this side, and I say, coloring, do not come down. Do not, I say, do not. Well, it's coming down. Somebody says, oh, you cannot fight nature, Professor. No, I am not fighting nature. I am collaborating with her, and now it is migrating back. There it is, and I could drive it the other way. So we are talking about convection. Convection, the transfer of heat energy by actual transfer of stuff. Remember, in an earlier program, I talked about conduction, which takes place in solid things like metal rods and wooden rods and the like. Now I am talking about convection, which takes place in fluids, because something must flow, and fluids is the generic name for gases and liquids. So we have this strange business of convection. Another illustration of it, an imaginary experiment. Imagine that I am sitting here smoking a cigarette, which I don't do because I don't smoke. So this is the real part of the experiment. And here I have a reading lamp throwing some light on a physics book. And the lamp is lighted. Question, where does the smoke from my cigarette go? Up here? No, strangely enough, it does not go up here. It goes up under the lamp and out from under the shade. Why? Because the heat of the lamp gives rise to a reduction in the density of the air, and a convection current is set up. Now, regarding this convection, I would remind you, a massive piece of business, because when we have convection on large scale in nature, what do we have? Gales and hurricanes and tornadoes. Fantastic energy in the moving air. And yet, consider the moving air. I tried to grab it. As I am led to say, there ain't nothing there. But oh, it is amazing. There are 3 times 10, listen to this, 3 times 10 to the 19 molecules of gas in a cubic centimeter of air. Incredible. An illustration of how big this number is. Supposing you and I and a million other people went to the ocean side and picked up that many grains of sand, and we piled them all up in a pile. How big a pile do you think we'd have? We'd have a pile that is 1 mile wide, 1 mile long, and 1 mile deep, a cubic mile of sand. And as I am given to say further, so you get an idea how big this number is, you know, I'm talking about there ain't nothing in air. 3 times 10 to the 19 grains of sand. Supposing you could count 10 per second. 1 to the 3, 4, 5, 10. 1 to the 3, 4, 10. How long do you think it would take to count that many grains of sand? Answer, 100,000 million years. And I say, ain't that something? And there is nothing here to grab. Incredible. More on convection. A beautiful demonstration. I'm going to light a candle here. I'm going to light a candle. And here I'm going to, and it rests in a little saucer. I'm going to put this glass tube on top. And now no air can get in at the bottom, and the candle flame will soon expire. It will asphyxiate for want of air to breathe. Watch it. It's getting light. It's getting dimmer, dimmer, dimmer. Now I'm going to put in a partition. Watch it. Well, I'm having a little... There it is. There it is. It has been revived. It has been revived. Let me take it out, and I assure you the candle flame will go out without this partition. Watch it. Watch it. It's on the verge of going. It's on the verge of going out. On the verge of going out. Yeah, and I'll catch it now and give it a new lease on life. There it is. And what must we say? Well, the physics is clear. I put a partition in this chamber, in this chimney, so that cold air could fall down and the hot air come up. Now, don't ever say that hot air rises, because that ain't so. There ain't no Hindu levitation in this business. What happens is that the less dense air is pushed up by the colder air. Convection. Convection. Oh, a beautiful thing to witness. Have you not seen seagulls, especially seagulls, soaring at certain places in the sky? I once did this in class, and I'm led to tell you, I said to the class, how many see that I'm a bird on the wing? A bird on the wing. And one fellow, not so poetic-minded, said, Professor, you look quite like a vulture. I thought that was terrific. The fellow had an idea, didn't he? Right. All right. So much for convection. Actual transfer of heated stuff as compared with conduction, which is transfer of heat energy alone. Now, on an earlier program, I spoke about conduction and got a little cut off because of time. I want to go back to one of those experiments. Here is a metal hub from which emanates a number of spokes of different materials: brass, copper, iron, aluminum, zinc, nickel, and so on. And here is a wonderful experiment to do. Here's what I do. I take a little steel ball, and with a little bit of soft wax, fix a ball to the end of each rod. A ball to the end of each rod. Now what do? I apply some heat energy from a burner to the hub. The different rods conduct the heat energy at different rates, and obviously the little balls fall off in an inverse order to the conductivity. But an interesting question arises. I have here two identical kinds of rods, an iron rod, an iron rod. They are absolutely alike in their composition, but they differ as follows, and this is a wonderful exercise. They are identically long, but one is skinnier than the other. As a matter of fact, one has that diameter and the other that diameter. This is a diameter D and that's a diameter 2D. And the problem is as follows. Supposing I put a little ball on the end of each, and what do I have? I heat the hub. And in what order do they fall off? Well, I'm going to tell you. Let's look at them, because it's a very difficult problem. This has twice the diameter, therefore it has 4 times the cross-sectional area. 4 times. Therefore it conducts heat away 4 times as fast. But because it is twice the diameter, it has twice the circumference, and therefore it radiates from the surface at twice the rate. So this one does not gain over this one 4 times, but rather only 2 times. So what do? If I put a little ball on the end of this one, no, correction, in the middle of this one, and on the end of that one, they will fall off at the same time. And I hope I've said that correctly, but I got a little fouled up. Indeed, if I said it wrong, then you will write me a letter saying, Professor, what you said was not right. What you said was not right. Notice, I've got a little perspiration in my eye. That is a sort of saline, and it is not pleasant. More on this business of conduction. A wonderful demonstration which you can do. A silver dollar, nice and clean. You put it tightly under a handkerchief, so. Tightly under a handkerchief. There it is, tightly. Now, I wish I had a cigarette. We will imagine that I have a lighted cigarette. This piece of clothes on. Lighted cigarette. I put the lighted end of the cigarette tightly down on the handkerchief, on the coin. Question, what happens? Nothing. Why? Because the clean silver underneath takes the heat energy away, as it did in a certain experiment I did with a wood and metal rod, and the handkerchief is untouched. This is a beautiful little experiment to demonstrate to your kin. Enchanting. Enchanting. Next demonstration. This one you can do. Remember I said what happens first when you put a thermometer into hot water? It shows a diminution in the column. Take a flask like this, fill it with water, put some food coloring in it, fit it with a 1-hole stopper in a glass tube, and the level is right here, more easily seen than the action of a thermometer. Submerge this in a vessel of hot water, and what do you see? Down it goes, for the reason that the glass vessel is heated first and expands. This concludes my recitation, and I thank you for listening. How do you do, ladies and gentlemen, and boys and girls, and mothers and fathers and people? I'm Julius Sumner Miller, and physics is my business. And we come once more to the subject of heat energy transfer. In an earlier program, I talked about heat energy transfer by conduction. And then I talked in another program about heat energy conduction by the mechanism of convection. And let me remind you that for conduction, we have, say, a metal rod. Nothing goes, no stuff moves very far. Energy is what goes. But in the case of thermal energy transfer by convection, we had the actual motion of stuff, like hot air and hot liquids and stuff. So in these two, we had transfer where there was something. Now we come to heat energy transfer by the mechanism of radiation. And this is a puzzling sort of thing, because it works best, as I like to say, where there ain't nothing. For example, the heat energy of a star called the sun comes mostly through empty space. So, radiation. Consider the following. Quite a marvelous thing to contemplate. Here I have an incandescent lamp, and I'm going to excite it momentarily, that is, connect it and energize it so it burns, it lights. Now watch what I'm going to do. I'm going to connect it, put my arm here, and I felt it hot right away. But that is still cold. That's a marvelous thing. So the radiation from that lamp reached my arm over this distance of a foot, which isn't very far because this radiation travels at the velocity of light, which is about 186,000 miles per second. So it didn't take very long to get to my arm. Still, the glass did not have enough time to be thermally excited and to warm up, as we say. So my arm was warmed by radiation. Another demonstration. Several programs of mine, and this one also, have opened with this little radiometer. And I am led to say to you that although this is a commonplace little device, would you believe it, it has not yet been thoroughly understood. So I invite you to go to the physics literature and read about it. There have been at least 1,000 notes in the journals written about this, but I will say a word about it. I am covering it from the radiation from the lamps in the studio, and when I remove my hands, we will find that its speed has slowed down very, very much. Then when I expose it to the radiation, its speed will pick up. Now, the vanes in this little rascal are very light and blackened on one side and shiny on the other. And if you look circumspectly at its method of rotation, you will find that the black faces always retreat from you, the observer. Now, I'm going to take my hands away. Look how slow it is. And look how much faster it's going. Very much faster. And the black faces are retreating. Now I have another one here. And this one isn't going, well, I excite it a little mechanically. That one isn't going at all. And I leave that as a puzzle for you. Why isn't this one turning? Why isn't it turning? You see, I consider raising paradoxes and dilemmas and uncommon questions much more virtuous than just talking answers. Next demonstration, which is a most unreasonable thing. Very unreasonable. Indeed, reason is ravaged by this demonstration. We will look first at 3 cans that I have. I have 1 can, 2 cans, 3 cans, and to begin with, they are identical. Here they are. Here they are, 3 cans. From fruit juice, let us say. Now, one of them I left shiny. The other one I painted on the outside black. And the third one I covered with a very thin layer of asbestos. Asbestos. Right. Shiny, black, asbestos. Now, what am I going to do? A wonderful demonstration. I'm going to put some hot water in these to the same level in all 3 cans. Water, 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 and a cover, if you wish, with a hole in the cover, and put a thermometer in each one. A thermometer. We will imagine that I have it right here. Here is a little stick which we understand is a thermometer. Now, this is hot water. 140 degrees Fahrenheit, say, which is about the temperature which you take a bath. Now, question. I let these stay here on the tabletop, and as time goes, they cool off. In what order do they cool? Or more exactly, which one cools the fastest? Now, nearly everybody in the world says that the black one cools the fastest because black bodies are good radiators. Now, part of that is true, but that answer is not correct. I'm going to tell you a strange thing. Because I am a kind-hearted fellow, I'm going to tell you. But having told you the answer, there is a greater mandate upon you to find out why it is so. Here it is. The one that is covered with the asbestos cools the fastest. Now, who'd have thunk it? That verb is the past pluperfect subjunctive of the verb to think. Who would believe that the one that's covered with asbestos would cool the fastest? And yet it does. And I will give you a hint. The program today, this program, bears on the subject of radiation. And therein lies the secret. So, shiny can, black can, asbestos-covered can, thin layer, very thin layer. Another commentary. Here I have a fourth such tin can, and I have put 7 layers of that asbestos. 7. And this can is brought down to the property of the shiny one, which is an amazing thing, absolutely. No one believes it. Next demonstration. The case of the 4 thermometers. Notice the title I give it. This is not a case for Sherlock Holmes, but for Julius Sumner Miller. Problem. I have here 2 identical thermometers. 2. Absolutely identical. This one, however, is painted white at the bulb, and this one is painted black. Now we will imagine that I go out into the sunshine, into an open field, with these 2 thermometers. To begin with, they read the same temperature. We let a little time elapse. Certainly, they show a rise, an elevation, a growing temperature. Question, what exactly do we see? Now, when I ask this, very few answer it correctly, but I'm going to tell you, again, because I'm kind-hearted. This one, the black one, shows an elevation much quicker, faster, sooner than the white one, but after a while, they come to thermal equilibrium with themselves and the surroundings and read the same temperature. So, having told you about a white thermometer and a black thermometer, I'm going to raise another question. Here I have 2 identical thermometers, and they are wrapped at the bulbs with cotton batting. Here you see the cotton batting is very tightly fixed. Here it is very puffy and loose. And what I want to say about these is this, that the same weight of cotton batting is here as is here. So the same amount of stuff insulates both of them. Now I go out into the sunshine with these 2 thermometers, and I ask you, what do they show immediately? And this is a wonderful thing. And I'm just wondering if I'm kind enough in my heart to tell you, because I've told you so much already. I'll leave this for you to explore. But let me say that this is why, for example, it is on occasion useful to wear clothes that are not too tight-fitting. And I have given you a hint about these 2 thermometers. More on radiation. The so-called thermos bottle, a Dewar flask, Dewar, D-E-W-A-R, Dewar, James Dewar, an Englishman. How is this made? Well, I'm going to show you. It is a glass bottle with 2 walls, an outer wall and an inner wall, closely sealed tightly, and the air between is taken out. And if we could see very sharply there, I'll play that to the camera, there is a little tip of glass where the vacuum pump has been connected. It's very difficult to see. Let me see if I can get another one. Oh, yeah, may be able to get this. There it is. There's the tip of glass, sealed off, with the air between mostly taken out. Now, a question I like to ask. You see these little pads of felt. There's one there and one and one. And I ask, where are they? They are not on the outside. They are not on the inside. No, they are between the two walls of glass. So as one might say, they are on the inside of the outside or the outside of the inside. Now, to more properly finish such a container, we silver it also on the inside as well as on the outside. Why? To minimize the radiation losses. Indeed, as you know, we can put some stuff in which is cold and it stays cold, or we can put some stuff in which is hot, which stays hot. So we have talked about radiation. And now I have a classical problem which you can investigate in a private way with much fun. Problem. Problem. I call it the problem of the black coffee. Here it is breakfast time. Breakfast time. I pour me a cup of black coffee. Here I am pouring a cup, and here is the cup of black coffee. Now I am a user of cream in my coffee. So I am on the verge of adding cream from the pitcher, and let us say it's cold cream from the refrigerator. I'm about to put the cream in the coffee when the phone rings. Ding! Now I have to go answer the telephone. And I expect, of course, to be delayed a little time. Question. I want to find my coffee as hot as possible when I come back. Should I then add the cream before I go to answer the phone, or should I wait until I come back? See, they're a beautiful thing. And I wonder if I should give you a hint. The hint is this. It depends also on this business of radiation. And I want the coffee to radiate away its heat energy at a lesser rate. And therefore, I should add the cream at some time in this discussion. So, you see, ladies and gentlemen, this business of thermal energy, incredible. And when one talks about radiation, he has to have in mind the large-scale view of our entire electromagnetic spectrum, which includes the visible, only a small part of the whole region, the infrared, radio waves, electric waves, ultraviolet, X-rays, gamma rays, and as I am led to say, who knows what is beyond. And I thank you for listening.
The boom towns of the West were populated by merchants, speculators, saloon keepers, and assorted hangers-on. They would spring up overnight and sometimes disappear just as quickly. A community of canvas huts, false front tents, and collapsible buildings. These were the tent cities of the American frontier.
Very few things were permanent on the American frontier. The railroad inched forward every day, new discoveries of gold and silver, and this called for a special kind of businessman, a flexible and mobile businessman. Hi, I'm Merlin Olson, along with Charlie Jones, and we're sitting in front of a typical tent city.
And Merla, this is a tent city that might not have been here yesterday and may not be here tomorrow because the businessman on the frontier had to go where the action was.
And location was everything. The man whose business was closest to the pay wagon or closest to the mine entrance, he was the one that earned all the money.
A tent city was a haven, a small oasis in the rugged and barren wilderness where friendships and rivalries developed quickly, where partnerships were often forged by mutual suffering or common danger. If we could resurrect the street sounds of that day, we might be able to identify boots on a board sidewalk, bottles clinking against glasses, creaking wagons, laughter and shouting. And the scraping of knives and forks on the ever-present tin plates.
In addition to the quick buck artists that populated these tent cities, there were many honest businessmen who set up laundries, bakeries, hotels, banks, blacksmith shops, and perhaps in this vast wilderness, most important of all, a place to get away from your own cooking. The construction of these towns was so flimsy that if a bullet was fired, and this happened quite frequently, it might go through every building along the street before coming to a stop. Many of these tent cities served as support bases for the railroad and were nicknamed collectively hell-on-wheels towns. Offloaded at each temporary end of track, they flourished for a few days or a few weeks and then moved on with the ever-lengthening railroad.
They didn't have franchises along the American frontier as we now know them. But if they had, then the Red Cloud Saloon would have been among the most popular at the tent cities. Merlin is inside, and this is the way it might have been.
For an Englishman, he's not too bad.
You fellers handy up, all of you.
It's a lousy day it is.
What do you got to drink?
Whiskey's $1 a shot. Wine's $2.50. Imperial champagne $3. Beer's 50 cents a draw.
Beer cold?
Well, had ice 2 months ago.
Prices seem a little steep to me.
You can always go down to the big tent,
How far is that?
30 miles.
Yeah, no opener. Not open. Open? I'll just have to give you your cards. How many would you like?
The man getting that card game over there?
I'm sure they'd love to have your money.
One, and he's got another
Hit
house.
me with 3.
Oh, 3 big ones. Here they are. Lucky
I think I'll pass.
Some of these temporary locations like Cheyenne, Laramie, or Julesburg would later become towns. But tent cities were like transit circuses, constantly moving, setting up and tearing down, as they kept pace with a rapid expansion on the American frontier. This vast land demanded strength, courage, and tenacity. Those who accepted its challenges and survived were the men and women who tamed the American frontier.
That sound, echoing across the prairie, heralded the advancing bands of iron that were to eventually tie this nation together, the Transcontinental Railroad. One of the great engineering feats of world history, an accomplishment destined to change forever the face of Western America.
This is Charlie Jones and Merlin Olsen. They said it was impossible to build a transcontinental railroad, and it might have been without a special breed of men. They were gamblers, willing to bend the law, to bribe every state and local official that they met. But they did it. They built the Transcontinental Railroad, and the payoff was well worth it. More than $100 million in land grants and bonds, and just as important, commercial control